Hello and welcome back to Set Theory. Today we're going over ordered pairs. So we already have unordered pairs, right? Because A and B are sets, then we can form this set by the axiom of pairing. But notice it's an unordered pair because the order that we write A and B in doesn't matter. We get the same set. But what if we wanted to find ordered pairs? And the important property that we want ordered pairs to have is that two ordered pairs are equal if and only if the first guy equals the first guy and the second guy equals the second guy. So example, we want the ordered pair 1, 2 to be different from the ordered pair 2, 1, since these guys are not equal to each other. But here's a question. How are we supposed to define ordered pairs when all we have are sets? Because remember, in ZFC set theory, every object of our universe has to be a set. So therefore, numbers like 1 and 2 are really sets in disguise. And so ordered pairs are also going to have to be sets in disguise as well. Well, Mr. Kuratowski right here in 1921 came up with a cool idea. Kuratowski said, define an ordered pair to just be this set. And then he proved as a theorem that if this is what you mean by ordered pair, then two ordered pairs are equal if and only if the first guy equals the first guy and the second guy equals the second guy. Now, it's important to note that different mathematicians, such as Norbert Wiener as well as Hausdorff, gave different definitions of ordered pairs. However, Kuratowski's definition is the most mainstream, and it's the one we'll be using for this course. So let's prove this. Well, the backwards direction is super easy, right? Because if these guys are equal, then you can just substitute C in place of A and D in place of B. And so, of course, these ordered pairs have to be equal. So let's prove the forward direction. Assume these ordered pairs are equal, and we want to show that A equals C and B equals D. How do we do that? Well, since we know this is true, we can rewrite it using the definition of ordered pair. Since these sets are equal, we can take the arbitrary intersection of both sides. And just a reminder, you got to be careful not to take the arbitrary intersection of the empty set because otherwise it's undefined. However, these sets right here are clearly not the empty sets, so we don't need to worry about that. But now we can simplify this. The left side simplifies to this guy intersect this guy, and the right side simplifies to this guy intersect this guy. The reason for that is that in lecture 1.6, we proved a theorem which says if you take the arbitrary intersection of something that looks like this, well, it's just this guy intersect this guy. Now, whenever you take the intersection of two sets, but one of them's a subset of the other, you just get the quote-unquote smaller one. So this intersection simplifies to singleton A. And by similar logic, this just simplifies to singleton C. And now, since these two singletons are equal, what's inside must also be equal as well. So we proved A equals C, so okay, we're halfway done. Since we know that A and C are equal, now let's replace all these C's with A's. And so we want to show that B and D are equal. Well, since these guys are equal to each other, then their arbitrary unions must be equal to each other as well. But what is this? This just simplifies to first guy union second guy. In other words, singleton A union this guy. And likewise, this arbitrary union simplifies to this guy union this guy. So singleton A union A comma D. Now, whenever you take the union of two sets, but one of them's a subset of the other, the answer is just going to be the quote-unquote bigger one. So this simplifies to A comma B. And by the exact same logic, this guy just simplifies to this, A comma D. Now, since these two sets are equal, they must have the exact same elements, right? So since B is in the first set, it must also be in the second set as well. So since B is in the first set, it also has to be in the second set as well. So that means either B equals this guy or B equals this guy. Now, what do we want to show? We want to show that B equals this guy. Well, towards a contradiction, assume that what we want to prove is false. Assume B and D are not equal to each other. Well, if B and D are not equal to each other, since we know that at least one of these has to be true, if this one's false, then this one has to be true. So since B is not equal to D, we must have B equal A. But if B equals A, then guess what? This set right here is just singleton A. So the left-hand side just simplifies to singleton A comma singleton A. And we can simplify this even further, right? Because since these two guys are the same, the left-hand side just simplifies to the singleton containing singleton A. Now, since these two sets are equal, they have to have the exact same elements, right? So since this guy is an element of this set, it also has to be an element of this set. So this guy is an element of this set. Now, since this guy is an element of a singleton, it has to equal whatever inside. So this guy has to equal this guy. Since these two sets are equal to each other, they have the exact same elements. So since D is obviously an element of this set, it has to be an element of this set as well. And since D is a member of this singleton, that means D has to equal A. But earlier we said B equals A, right? So therefore, by this and this, we have that B must equal D. And that's a contradiction, right? Right? Because we assume that B was not equal to D, but we prove that B equals D. So therefore, our assumption was wrong. Since our assumption that B was not equal to D was wrong, we must have B equals D after all, which is what we wanted to show. Okay, so we proved that this has all the properties that we wanted ordered pairs to have. Although it might be a little awkward thinking of ordered pairs as an ugly set like this, nevertheless, as long as it behaves the way we expect ordered pairs to behave, most mathematicians don't really care. Okay, now here's a question. Let's say we're given an ordered pair P, but we don't know what A and B are. Was there a nice formula that takes P as input and spits out the first coordinate as output? And what about the second coordinate? Is there a nice formula that if you plug in P, you get B as output? Well, it turns out that finding the first coordinate is pretty easy. All you have to do is take the arbitrary intersection of the arbitrary intersection of the ordered pair, and you'll just get the first coordinate. Why is this true? What's this inner part? What's the arbitrary intersection of A comma B? Let me write it like this. Well, the arbitrary intersection is just going to be this guy intersect with this. So singleton A intersect with this guy. All right. Now, since this guy is a subset of this guy, when you take their intersection, you just get this one. You get singleton A. All right. Now, if you take the arbitrary intersection of a singleton, you just get whatever inside. This was a theorem we proved in lecture 1.6. But remember, singleton A is just this guy, right? So we proved that the arbitrary intersection of this guy has to equal A. Now note that we could have changed this outer intersection to a union and we'd still get A. The reason for that is that this part would still be the same singleton as before. And whenever you take the union of a singleton, you just get whatever's inside, namely A. Although I believe the Wikipedia page gives this formula, I actually like this one better because I think it's easier to remember since it's just intersection, intersection. You don't have to remember what order these two guys go in. So now for future reference, if P is an ordered pair, we can just define the projection of P onto the first coordinate to be this guy. So we take an ordered pair as input and our output is just the first coordinate. And we can do this even if we don't know what A and B are ahead of time. So here's an exercise. Let's try finding a similar formula that takes an ordered pair as input, but instead of giving us the first coordinate, it gives us the second coordinate. And spoiler alert, it's not going to be pretty. So suppose P is an ordered pair. Well, by similar logic as earlier, the arbitrary intersection of P is just the intersection of these two sets. So we get this guy. And the arbitrary union of P is going to be the union of these two sets. And since one's a subset of the other, we get the quote-unquote bigger one. So we get this guy, A comma B. If you take the set difference of these two guys, you should get A comma B difference singleton A. Now, the rookie mistake is to assume that the set difference just simplifies to singleton B. However, that's not always true. It depends if A and B are distinct or not. If A and B are equal to each other, then this set is just really singleton A in disguise. So this becomes singleton A difference with singleton A. And whenever you take the set difference of a set with itself, you just get the empty set. But what happens if A is not equal to B? Well, if A is not equal to B, then this simplifies to singleton B. Why is that? Well, show two sets are equal, we just got to show that they're subsets of each other. The reason this guy's a subset of this is that if you're in this set, But that means you're in this set, but not in this set. In other words, you have to either equal A or B, but you can't equal A. So therefore, you have to equal B. And therefore, you have to be in this set. Okay, so that shows this guy's a subset of this. But how do we know this guy's a subset of this? Well, this guy has only one element, B, so we just got to show that B is an element of this guy. To show B is an element of this guy, we got to show B is in this guy, but not in this guy. Well, we know B is in this guy, obviously, right? And likewise, we know that B is not in this guy. Why not? Because we know A and B are distinct, and the only thing in this guy is A. And here is where it's very important that A and B are not equal for this to work. Okay? So using this, we could write a piecewise formula for singleton B. If A and B are distinct from each other, then singleton B is just going to be this guy, right? But what about the other case? What if A and B are equal? Well, if A and B are equal, then singleton B is just the same as singleton A, right? But now we can rewrite this because singleton A is just this guy right here. So let me copy paste that. And now this condition A is not equal to B. Is there a way I can rewrite that without having to use A and B? Well, yes, I can. Notice that A is not equal to B if and only if this guy is non-empty, because this guy is some singleton, some non-empty set if A is not B. But if A equals B, then this set difference is the empty set. So you can replace the condition A is not equal to B with saying this guy is not equal to the empty set. All right. Now, if we have a singleton, but we want to find what's ever inside, we can just take the union of that singleton, right? But what's the singleton? It's really this ugly expression, right? So we can copy paste this. Let me cut off that top part. So here's our ugly expression for B, just in terms of P. And it might look like I'm cheating by using piecewise functions. However, if you watch my previous lecture, you'll see that anything that we can write piecewise can in principle be written as something that's not piecewise, although it's going to be ugly. All right, so for future reference, if P is an ordered pair, we can define the projection of P onto the second coordinate to be this ugly guy. In other words, this guy is just the second coordinate of P. So if you put in an ordered pair as input, it spits out whatever the second coordinate is. And by the way, you don't need to memorize this ugly formula, but it's kind of cool that at least in principle, there is some formula out there. Now I want to talk briefly about other definitions of ordered pair. Now, Mr. Kuratowski here wasn't the first one to come up with a definition of ordered pair in terms of sets. For example, Felix Hausdorff even earlier gave a different definition. He defined an ordered pair to be this set. It turns out that if you use Hausdorff's definition instead, it still satisfies this important law. Let's try to prove it, although I'll write a little h for Hausdorff just to be super clear which definition I'm using. The backwards direction is trivial because if A equals C and B equals D, then you can just substitute C for A and D for B. And then, of course, this has to be true. So let's prove the forward direction. Assume these two ordered pairs are equal using Hausdorff's definition. In other words, these two sets are equal to each other. All right, so how do we show this equals this and this equals this? Well, you might think, well, just look at which set contains 1 and somehow use that to match these two sets together. But the problem is that if B equals 1, then both these sets will have a 1 in them, and that makes it confusing. So let's proceed by cases. For our first case, assume B is not equal to 1. So that means 1 is not an element of this set, right? Because 1 and 2 are distinct. Now, since these two sets are equal, they must have the exact same elements. So since this guy's an element of the first set, it has to be an element of the second set as well. So that means B comma 2 either has to equal this guy or it has to equal this guy. However, it can't be this guy because 1 is not an element of it. And so therefore, this guy has to equal this guy. So this guy has to equal this guy. So that means B has to be in this set, which means that B either has to equal D or B has to equal 2. But what happens if B is 2? Well, if B is 2, then the only thing in this set is 2. So therefore, since D is in this set, D has to equal 2. So if B is 2, then D has to be 2 as well. All right, so we've shown that either B has to equal D or B has to equal 2. But if B equals 2, then B and D have to both be 2, so they have to equal each other anyway. So in either of these two cases, we get B equals D. So B equals D no matter what. And since we know this is true, we can substitute. Let me change this D to a B. All right, now since these two sets have the same elements, then that means this guy has to be in this set. So this guy right here either has to equal this set or it has to equal this set. However, it can't equal the second set because the second set doesn't have a 1 in it. Remember, we said 1 is not an element of it. So that means this set has to be this guy. So these two sets have to be equal. Since A is in this set, it means either A has to equal C or A has to equal 1. However, in the case that A equals 1, then this becomes a singleton. It only has one element, 1. And so since C is an element of this set, then in that case, C would have to equal 1. So if A equals 1, then C has to equal 1 too. So in either of these two cases, we get A equals C. All right, so A equals C, and earlier we said B equals D. Okay, and that's what we were trying to show, right? All right, so we've proven the theorem for the special case that B is not equal to 1. Now let's try another case. Let's try to prove the theorem now for the special case that B does equal 1, but A is not equal to 2. Well, we still have this, right? Since we're assuming B equals 1 this time, let me change that B to a 1. Since we're assuming that A is not equal to 2, then that means this little set right here doesn't contain 2. And since this set has to be in here, meaning it has to equal this set or this set, well, then obviously it has to equal this set, right? Because the other one contains 2. So these two sets have to be equal. And also this set has to be in here, right? So it has to equal this guy or this guy. However, it can't equal this guy because this guy doesn't contain 2. So the only possibility is it has to be this guy. So therefore, this guy has to equal this guy. Now, since 1 belongs to this set, and since 1 and 2 are not equal to each other, then 1 has to equal D. So this tells us that D equals 1. In particular, since we're assuming B equals 1, then that means B and D are equal to each other, right? Because they're both 1. So we've proven that B equals D. But now this equality right here implies that A has to equal C. Why is that? Well, either A has to equal C or it has to equal 1. If A equals C, then we're done. But if A equals 1, then this becomes 1 comma 1. So it's a singleton having only one element. And since C is in the singleton, then C also has to equal 1. So in that case, if A is 1, C is also 1. So that means A has to be C anyway. All right, so we've proven that A equals C and B equals D, which is what we wanted to show. All right, so we've proven the theorem for the case B is 1 and A is not 2, and we've proven it for the case that B is not 1. The only possibility that remains is to prove it for the case that B is 1 and A is 2. So what happens if B is 1 and A is 2? Well, if A is 1 and B is 2, we still have this, right? But now we can substitute. A becomes 2 and B becomes 1. And notice that both of these sets are equal. That means this set is really just a singleton in disguise. Since these two sets are equal, then that means this guy has to be a member of this set. In other words, this guy has to equal 1 comma 2. So this guy has to equal this guy. But since 2 has to either equal this guy or this guy, but can't equal this guy because 1 and 2 are not equal to each other, then 2 has to equal C. So C has to be 2. And since we're assuming A is 2, that also tells us C and A have to be equal. By similar logic, this set has to equal this set. So these two sets must be equal. And so 1 either has to equal D or it has to equal 2, but it can't equal 2, right? So it has to equal D. So D is equal to 1. And since we assume B is equal to 1 as well, that means B equals D. And there we go. Okay, so we've proven that in all three of these cases, no matter what happens, A has to equal C and B has to equal D. So the moral of the story is, whether you use Kuratowski's definition or Hausdorff's definition, ordered pairs still behave the way that we would like them to. I think the reason Kuratowski's definition is mainstream is because it's a little nicer. Hausdorff's definition is a little bit ugly in that it requires these quote-unquote anchor points, 1 and 2. And these seem a little arbitrary, right? The only properties of 1 and 2 we use in the proof is that they're distinct, but that's it. So for example, if I replaced 1 with the empty set and 2 with omega, this theorem would still be true. What's nice about Kuratowski's definition is it doesn't require these two anchor sets ahead of time. It's just dependent on A and B. But in any case, Kuratowski's definition is the mainstream one. It's the one we're going to use to build all of math. Like and subscribe if this was helpful, and I'll see you in the next lecture.